Hi, welcome to this video. In this video, I'm going to briefly talk about Chapter 7, the time value of money with single payment value. I'm just going to briefly go over the slides and make some emphasizes on a couple of slides that are especially important. I hope after watching this video, you can better understand this concept in this chapter. I just want to emphasize before I start that this video is not a replacement or a substitute of the reading of the chapter. I just bring out important ideas throughout the slides, but rather the comprehensiveness of the ideas are going to be presented in the book readings. So if you think about it, time value of money is a pretty straightforward idea. That is to say, given the choice between receiving a dollar today and receiving a dollar a year from today, most people will prefer the dollar today. And why is that? The reason is that a dollar 1 year from now is not worth as much as a dollar today because we can simply put the money in a bank account and get more money a year later. So it's just always a better choice. So the reason behind this choice, or in other words, why does putting money in the bank will give you a better amount of money or give you a larger amount of money is basically because at least inflation or rising prices erodes purchasing power. For you to give money to the bank for giving up your consumption today, you have to be compensated. So as a result, the bank is going to promise a risk-free, which is low, yet stable and positive interest rate. So what would it take to make you indifferent to either a dollar today or a dollar in the future? Interests and time value of money concepts link the present value of a dollar to the future value of a dollar. The present value is basically the value of the money right now, today. The future value of a dollar is basically how much does the $1 equivalent to or worth 1 year or sometime in the future. If inflation ran at 3% annually, but someone promised to return a dollar to you after a year with 3% interest, you would be made whole, right? You would be the same way. You would be indifferent. In other words, to receiving either that present value of a dollar or 3% interest plus the dollar in the future, you're equivalent, you're indifferent. Though inflation would erode the purchasing power of the dollar by 3%, the 3% interest you would earn would offset the erosion of the dollar's purchasing power. Sometimes future cash flows are organized, predictable, and uniform. When you receive a fixed regular payment into the future over a specific period, you have what is called an annuity, which will be discussed in the next chapter. So basically, an annuity promises you a fixed amount of money over a certain number of years. And usually the payment is made annually, so it's usually called an annuity. Most of the time, however, cash flows are not orderly. That is to say, there's some randomness in the cash flow, and the pattern is really not predictable. How to calculate the present value or the future value of such cash flows are going to be introduced in the further chapter. When in doubt, evaluate individual cash flows as separate lump sum cash flows in order to make sense of them. A single lump sum present value will grow into a future lump sum value through the process of compounding. The idea of compounding is very, very important because most of the real-world applications or financial products assumes compounding interest. Let's look at some numbers. If you invest $1,000 for 1 year, that investment generates 5% interest, your investment will worth $1,050 at the end of the year. That's a total, or that's the sum of the 1,000 initial investment plus the 5% of additional interest of $50. The way we calculate this $1,050 is that we take 1,000 and multiply it by 1.05. So how can we understand this 1.05? What does this 1.05 mean? This 1.05 is nothing more than 1 plus 5%. And 1 plus 5% is exactly the amount of money you're going to get if you invest $1. In other words, for every dollar you invest in this investment, you're going to get $1.05 a year later. If you put in $1,000, it's going to be 1,000 times this 1.05, which is $1,050. If you were to invest $1,000 at 5% per year for 5 years, and you let the interest compound, you would get this number, which is 1,276 and 28 cents. The math behind this is that 1,000 multiplied by 1.05 5 times. So equivalently, it's going to be 1,000 multiplied with 1.05 raised to the power of 5. So why do we do this? You can imagine this as a 5-year process. In other words, instead of making this one 5-year investment, you make 5 1-year investment, and each investment will give you 5%. In other words, at the end of the first year, you're going to get $1,050, right? It's 1,000 times 1.05. And then a year later, you get $1,050 times 1.05, which is 1,000 times 1.05, and then times 1.05 again. That's equivalent to 1,000 times 1.05 squared. If I replicate this process, I'm going to end up with 1,000 times 1.05 to the power of 5. So why do we do this? How is this related to compounding? So this process of calculation is basically compounding. Remember, at the end of year 1, you got $1,050. And then at the end of year 2, you get $1,050 times 1.05. Why do we use $1,050 to multiply with 1.05 to calculate what we will get at the end of year 2? Why don't we just use 1,000? It is because at the end of year 1, since the interest is paid to you, which is $50, you do end up with $1,050, and you can put this $1,050 in the bank account for the second year. So as a result, at the beginning of the second year, you get a slight larger principal to begin with. And in the second year, instead of making $50 of interest as you did in the first one, you actually make a little more. How much more? That's going to be $50 times 5%. Okay, so in total, you do get a little more on the interest you reinvest. So that is called the interest on interest. And interest on interest is the reason why compounding is so important. If you compare compounding with simple interest, where you do not compound, in other words, at the beginning of each year, you only make up interest on the original $1,000, you're going to get $1,250, right? 5 years, 5% per year, $1,000 every year. So $50 every year. So that means $250 of interest at the end of year 5. So in total, you end up with $1,250. So that is a little less than 1,276 and 28 cents, right? It's about 25, 26, 28 less, right? $26.28 less. So it's about 10% of the total interest you get. So you do get some extra benefit. If you can calculate this on your own and try to see how the difference is if you invest 10 years, 20 years, or even 50 years. You're going to see that the interest become more and more pronounced as you invest longer and longer time. If we want to put everything we have talked about in a formula, that is like this: the future value of a lump sum money, of a present value of a certain amount of money, is the same as the present value times 1 plus the assumed interest rate raised to the power of n. Since we already have this formula here, I just want to emphasize that this formula is not just the formula for future value. This formula describes a relationship. That is to say, for a certain amount of money you have today, the future value of that money is calculated as the amount of the money multiplied with 1 plus the interest rate raised to the number of years that you're going to invest that money. But for a certain amount of money that you are promised to receive certain time in the future, which is future value. For example, if you are promised to receive $1,000 in the future, that is 10 years later, you can easily calculate its present value using this formula as well. Because again, this formula describes the relationship between present value, future value, interest rate, and the number of years of investment. With this formula, all the time value of money problems can be solved. Not just future value calculation, it can also solve the present value calculation, interest rate calculation, and number of periods calculation. The formula can be easily transposed and made to solve for any of the variables as a dependent variable if the other three independent variables are given. A best practice for solving time value of money problems is to create a table for each problem that identifies the known independent variables and the unknown dependent variables. That is the thing you're solving for. Setting up such a table will sort data so a financial calculator or Excel functions can be used. So let's look at how we can transpose this formula into a present value calculation. As you can see, in the previous formula, the future value equals to present value multiplied by 1 plus r raised to the power of n. So here, the present value is just future value divided by 1 plus r times raised to the power of n. This is the same formula as the previous one. This equation is transposed to highlight that we're trying to solve present value. Once again, this formula describes the relationship between present value, future value, interest rate, and n. So how is the discount rate calculated? So in reality, the discount rate is usually implied in the markets when we trade. We might know that the present value grows to a certain future value over a period of time, but we do not know what the implied interest rate can be for such an investment. This is in particular common when you're trying to invest in a debenture or in a bond. So we are investing in a bond, for example, a treasury bill. A treasury bill usually will be traded at like $95. Let's assume, for example, a treasury bill is usually traded as $95. And if you buy this $95 treasury bill, you're going to be promised to given $100 6 months from today. So what's the return of that? You know you're going to get $5 more. So what's your return? So the way to calculate is to use, again, another transposition of the formula we just saw. So if we were to invest $1,000 after 5 years, amount had to grow to $1,250. We would have invested our funds at a rate of 4.56%, which the same reasoning used to determine discount rates can also be used to calculate a growth rate. For example, if the population of Maldives doubles from 2,000 to 4,000 in 20 years, at what average annual growth rate is this growing? So this is basically saying you have 2,000 people as a present value, 4,000 as a future value, and you have 20 years to go from 2,000 to 4,000. So what's your per year average growth rate? If you plug in the formula, you're going to end up with 3.53%. We can also calculate the number of periods. The number of periods is pretty tough to calculate by hand because it involves some logarithm or log transformations. So as a result, a financial calculator or Excel functions are usually pretty straightforward. In this video, I'm going to not directly go through financial calculators. Instead, we're going to have a separate video on financial calculators. But what you can do in this specific example is that if you invest $1,000 at 5% and you want to get 1407 in the future, and you want to know how much time you need to get there, this is very important in retirement planning. For example, if you know you can save $20,000 per year and you can invest that $20,000 per year at 8%, and you want to retire with $5 million in your account, you can try to figure out using this formula how long you need before you can retire. What you can do in a financial calculator or in an Excel function is that you can enter present value as 1,000, future value as 1407, and R as 5%, and you can solve for N. So in this specific example, the answer is 7 years. Another important idea in time value of money calculation, as well as in interest compounding calculation, is that the frequency of interest compounding matters. If you invest $1,000 at 6% per year, and if you compound only once a year, you're going to end up with 1060, which is pretty straightforward. We have talked about that. But if you invest $1,000 at 6% per year, but compounded twice a year, that basically means every half year you get 3%. So the calculation is going to be like this. You're going to use 1,000 times 1.03, which is $1,030. This is what you get at the 6 month mark. And then you put that $1,030 in for another 6 months at 3%. Because 6%, 3% is just half of 6%. You're going to end up with $1,060.90. You got 90 cents more. So why 90 cents more? Remember our interest on interest discussion. 90 cents is exactly 3% multiplied with $30. Investing $1,000 at 6% per year, but if we compound every quarter, that basically means every quarter we get 1.5% of interest. We will end up with $1,061.36, which is $1.36 more than compounding once per year. So the compounding frequency really matters to our calculation. If we compound twice, that's basically saying we're investing in a 2-period product, and each period has half of the quoted interest rate. If we invest in a quarterly compounding product, that means for a year, that means we are investing in a 4-period compounding products, and each product we have a quarter of the quoted interest rate. The more frequent we compound, the greater the future value. And also, the more frequent we compound with the same future value, the lower the present value. In other words, the effective interest rate is much higher if we compound more frequently. So the relationship function can be adjusted for the number of compounding periods when compounding is more than once per year. If compounding is just one time per year, then R will just be the quoted interest rate and N is just number of years. But if we compound more than once a year, we just have to use the number of total periods as N. If you compound twice a year, then you use 2 times the number of years, that is the number of periods. And for R, we just have to use the periodical rate. In other words, if we quote 6% per year, that means 3% every half year, 1.5% every quarter, and 0.5% every month. All right, so that concludes this video. I hope this video is helpful. If you have any questions, please let me know.